Hello, this video covers all of the notes for 1.3. Most of this is information, or all of it's information that you've seen. I think the only good refresher would probably be maybe just like the horizontal line and vertical line stuff. Maybe like perpendicular lines, slopes, relationships, things like that. But for the most part, I think we should be in good shape with this. Nonetheless, we're spending time to go over it. So first off, starting off with slope-intercept form, we know is y equals mx plus b. We can easily see that m is the slope and b is the y-intercept. If we did, for instance, like an input-output table, very quickly we can see that if we plug 0 in for x, y would equal b. And when x equals 0, you're on the y-axis, so the y value equals b, so that'd be your y-intercept. And then again, if we did just an input-output table and looked at the relationship of the increase in y's relative to the x's, that would be equal to m. It's one way to easily see why slope-intercept form is what it is. So algebraically speaking, we saw this in 1.1, y2 minus y1 or x2 minus x1, or the difference of the y's divided by the difference in the x's. I'm sorry, ran out of room there. Graphically, rise over run is how we verbalize the graphical relationship from point to point, or the slope. And once again, as we just talked about, the y-intercept would be 0b, or uppercase B. Standard form, ax plus by equals c. A, b, and c are all integers. Typically, it's preferred that a is positive. I don't get too technical on that. If it's negative, I'm fine with that. Especially standard form is typically used for solving systems, and if, let's say, the coefficients of x are the opposite, one's like 3x and one's negative 3x, and we just add them together. But again, that's personal preference. Horizontal lines. Horizontal lines, if let's say we have a horizontal line going through a point x comma a. Let me switch over to black here. Say we have a horizontal line, there's our xy coordinate system. Say we have this horizontal line, and it's going through this point right here, x comma a. Well, if we moved over here, the x value would be different, so maybe we call that like x1, but this would still be a because we don't go up and down at all. Y value here would be a, etc. So therefore, a horizontal line, the y value equals a. Vertical line is very similar, and note I set up these coordinates nice, or I gave them variable names nice, that work nicely with the problem. So if we do a vertical line, same thing. If we're going up and down, only the y value is changing, but the x value is the same. So if this right here is the x value of a at that coordinate right there, where it crosses the x-axis or anywhere else, that means every value of x on the vertical line is a. So the equations of vertical lines is x equals a. So very, very simple. If they give you, say, there's a horizontal line through the point 2, 4, you just simply look at the y value, y equals 4, and then the opposite for a vertical line, you just look at the x value. Parallel lines are going in the same direction, so therefore their slopes are the same. They have the same rise over run, but their y-intercepts are going to be different, because if they were the same, they would be the exact same equation. Perpendicular lines have what's called opposite reciprocal slopes. And if you graph two lines that are perpendicular to each other, measure their slopes, you would see their opposite reciprocal, and then also we could go through a proof. We'd draw two lines, maybe create a right triangle out of that. Like we have this, so let's say those are our two lines. Something like that. Got these slopes. I don't know. Be interesting to explore if we have the time, but in any case, we do know that they're opposite reciprocals. and their y-intercepts are the same or they're different. Reason being, say if I have, say I got this as a coordinate system, and then I have two lines right here that are perpendicular. Well, they could be perpendicular here. Well, let's say if I take both of these, like this one, and I slid it over, I translated it over, but didn't change its slope, I could translate it over to here, for instance. It would still be perpendicular to this line, but would have the same y-intercept. See, I'm trying to get it to go through the same y-intercept. Over here it has different y-intercept, but it's perpendicular. So just the fact that we can translate lines in a parallel way and they are perpendicular, not the same slope, they can have the same or different y-intercepts. So an example of a slope of a line that's perpendicular, of two lines that are perpendicular, if I have 2, for instance, we can just make it a fraction, 2 over 1. First we can take its reciprocal, which is 1/2, and then the opposite of it, -1/2. So 2 and -1/2. Another example would be like if we had like 3/2, opposite reciprocal would flip the fraction and also turn it negative, or opposite. So those are some examples. A note up here, this was supposed to be on that first page with the 2 slopes for perpendicular. That's what that is. Okay, so let's get through some examples here. Find the slope, y-intercept, and graph of 3x minus y equals 16. So we have a line in standard form. So if we want to find the slope and y-intercept, obviously we need to be in slope-intercept form. So we're just going to want to solve for y. Subtract over 3x. -8y equals -3x plus 16. Divide by -8 on both terms. Write it like this. So that gives us -3 over -8, which turns positive. Let me get rid of that. So we have 3/8 x. Preferable to write the x separate when we're in slope-intercept form. We easily see the slope. So slope, I'm not going to write it out, but you just write out on the side, m equals 3/8, and then y equals -2. Graphing, go start with the y-intercept of -2, and then positive 3 over 8. Excuse me. Go up 3, 1, 2, 3, and over here. I'll do it with the cursor. Start here, go up 1, 2, 3, and then over 8. 1, 2, 3, 4, 5, 6, 7, 8. I think it was that right there. And you got your line. Just need 2 points typically. It's good enough. Okay, given a line through this with slope, find the equation in standard form. Well, if we're given a point and a slope, it makes sense to use slope-intercept, but we can also use point-slope, which looks like this. So you can put that maybe on the first page if you want. Sorry, I didn't have it there. Just a side note, that simply comes from slope formula. So I'll just quickly go through this. If you look at slope formula here, y2 minus y1 over x2 minus x1. If you just multiply this to the other side, then you move this to the left-hand side, so you have y2 minus y1, and then we have m multiplied by x2 minus x1, and the x1, y1 is obviously a specific point, generalized though, as well as x2, y2, that's a specific point, and we just, completely generalize that just by making y, meaning we're only going to be plugging 1 point into the formula or equation. There we have point slopes. That's pretty simple to come up or find where point slope comes from. So that being said, y1 is the y value of the point. The y value of the point is 4, equals the slope is 5, x minus -10. I'll just write it out explicitly. So simplifying this, we have y minus 4 equals 5. We're going to, first off, this is going to turn positive, so we'll distribute in the 5. 5x plus 50, and we want to get into standard form, so we want to move over the 5x term, so I'm going to subtract over the 5x plus y, and I want the constants all to the other side, so the negative 4 I'm going to add over to the other side, which would give us 54. Totally fine with that. Negative 5x plus y equals 54, and like I said, the standard practice is having a being positive, so if you did, then you just change it to 5x minus y equals negative 4. Okay, next one, given 2 points, find slope-intercept form. First we got to find our slope. So we have, go either way, negative 1 minus negative 3. Let's do it that way, negative 1 minus negative 3. And then we have 2 minus a third. It also works nice since the fraction second. Not that it makes it much easier, but maybe a little bit. So here, let me clean that up. So here, as I clean this up, I'll go ahead and talk through this. This is what we have is called a complex fraction, where we have a fraction within a fraction. And what we do is we look for the least common denominator among the 4 terms within the fraction. So the denominator of this is 1, right? Negative 1 over 1, 3 over 1, 2 over 1. This is 3, so the LCD is 3. So what we do is we take and multiply the top and bottom of the large fraction by the LCD of the smaller fractions, and that happens to be 3. So what's nice about this is the way that this lines up is if we just look at these numbers right here, this is being 3 is being multiplied into here, and note, because we're doing this 3 over 3, situated the way it is, this ends up going into the numerators of those smaller terms. Same down here on the bottom. So when we do that, and note, I have not found a case where when you have a complex fraction like this method does not work the most efficiently. It always works the most efficiently, as far as I've seen after teaching pre-calc, algebra 2 honors, etc. for 10 or more, 15 years, something like that. Never seen a case where this isn't the best method. Now this negative 1 plus 3, we could add those together, then multiply by 3, or you can distribute the 3 in, and I think I'm just going to distribute the 3 in just to kind of indicate the process, given their complex fractions we'll see later will get a little more complicated. So it'd be negative 3 plus 9. When I say the fractions will get more complicated, you won't be able to combine these terms before distributing in. So I'm just going to go in the practice of distributing them in just so you see what it looks like. Down the bottom, again, probably easier to distribute than to combine first. In this case, the top case it wasn't, but again, I'm just showing the technique. 3 times 2 is 6, minus, now remember this really is lined up with the third like this because this goes into the numerator. So I have a minus there, but then I have a third times 3 is 1. So it simplifies nice for us. On the top we have 6, on the bottom we have 5. So now we have our slope, so we have y equals 6 over 5. I don't think I made any errors there, like calculation errors. 6 over 5x, oh, we don't have the slope yet, or the y-intercept, excuse me. So let me get rid of this, and we can go to point slope form. I think is easiest. I use either point. How about 2, negative 1? So negative 1 goes in for y sub 1. So if I have negative 1 in there, minus negative 1 turns positive 1. My slope is 6/5. And then I have x 2 minus 2. So y plus 1, distributing the 6/5, x, and minus 12 over 5 when I distribute in the 6/5 times 2. Subtract 1 from both sides, cancels that out. And to combine these two, I'm going to multiply this by 5 over 5, so it's just a fraction 5 over 5. So I have 12/5 minus 5/5, get rid of that 1, it's 12/5 minus 5/5 is negative 17/5, and there's our slope intercept form. Okay, last one, find the slope of an equation, a line that goes through this point with a slope that's undefined. Sketch a line. Well, let's quickly look at slopes. This would be a slope, sorry, here we go. Slope 0 because we rise 0, horizontal line. We don't rise at all, we just run, so it'd be like 0 over 4, or 0 over 2. So horizontal lines have slopes of 0, and then we have a positive slope, and this would be a negative slope. Right, this would be the first one, this would be positive because rise would be going up for y and run would be positive for x. So positive over positive is a positive. Here, if we go from point to point, we go down, be negative for y, positive for x. Similarly, if we go up, which is positive for y, and over negative for x, a positive over a negative, or negative over a positive, is a negative slope. Now, if we go to a vertical line, and we just like at 2 points and find the slope between them, we would rise, but we'd not run at all. So we'd have some non-zero number in the numerator and 0 in the denominator. Any number other than 0 divided by 0, so 5 over 0, 2 over 0, and so on, is undefined, as we know. So therefore, if a slope is undefined, we know we have a vertical line. And what we know about vertical lines is x equals the x value of the point, because if this is the point, negative 10, 4, like the one given, and I go up, I go up, I go up, the y value is going to change, but the x value is going to stay the same. So therefore, the equation of the line is x equals negative 10. Sketch the line, would just be a vertical line. Well, let's go ahead and do it with a coordinate system. And over here, x equals negative 10.